This lecture we will learn about cover time. In the previous lecture we learned an important parameter of random walks, namely the commute time. Okay. So, commute time was denoted by CUV, and we said that this is a sum of two parameters HUV plus HBU. Okay. These were the hitting times both of them were hitting time, and HUV is the time taken to start at vertex u and reach vertex b for the first time, and HVU is the time taken to start at v and reach back at u. The sum of these was the commute time, and we had argued with the help of electrical networks that this quantity is equal to 2 times number of edges times the effective resistance between u and v. Okay, so, this is the number of edges and this is the effective resistance. We will now look at cover time. Cover time basically is the time taken to cover the entire graph or visit all the vertices. So, we will formally define what these are. This is denoted by C G x. So, here x is a starting vertex. So, this is a vertex. This is defined as time taken to visit every vertex at least once starting at x. So, imagine that we are doing a random walk on a graph, and if the starting vertex is x, the time taken to visit every vertex, assuming we start at x, that is known as the cover time or the expected time taken. So, the time taken will be a random variable, its expectation is called as the cover time. The theorem that we will show and will prove is cover time of a graph. Okay. So, cover time of a graph, which is by definition equal to max over all vertices x C G x. So, cover time is O n cube. Okay. That means, no matter which vertex you take, the expected time to visit all the vertices once, at least once, is O of n cube. Now, we will also show the following fact. There exist graphs such that C G is equal to theta n cube. Okay. So, we can construct one such graph. So, let us look at a clique. Okay. Here this is a clique on on 5 vertices. Let us say there is a clique on n vertices, and there is this line with n vertices. So, total 2 n vertices. And edges is equal to n choose 2 plus n. So, that we can say that it is approximately O of n square. Okay. Now, in this graph, the cover time is theta n cube. That is, if we start at a vertex, Of course, it depends on which vertex you start at. If you start at this particular vertex, let us call this vertex where the stem meets the cluster. So, this graph is a special name, this is called as a lollipop graph. So, if you call this as vertex u and this end as vertex v, if we start at vertex u, the time taken to visit all the vertices is O n cube. Okay. So, now a couple of things about cover times. Cover time is not a monotonic property with respect to the edges. That is, if you increase the number of edges, the cover time need not decrease. And if you take the complete graph, the cover time is n log n, approximately n log n. If you take the straight line graph, it is n square, and something in between we can have O of n cube. Okay. So, we will first show that if you start at vertex u and we want to travel, it will take O of n cube. Okay. So, in order to show that, we will take some results from our previous lecture. If you look at h u v plus h v u, that is the time taken to go from u to v and then v to u, that is the cover time, that we know is equal to, say, O n square. Let us write this as c times n square, c is some absolute constant. So, this is equal to 2 times the number of edges, which is c n square, times the resistance between u and v, which is about n. So, this is equal to O n cube. So, sum of two quantities is O n cube, that means at least one of them should be greater than n cube. In fact, if you start at vertex v and if you want to travel till u, this is a random walk which we have already explored, and we know that the time taken to do that. So, the first time you reach u will be the time taken to traverse this entire thing, and that is roughly, so h v u, this is O n square. While looking at the Markov chain for 2 SAT, we had explored this and showed that it is O n square. So, since the sum of these is O n cube, h u v should be, so this would mean that h u v is O n cube. What we will show in the remaining part of this class is that C g is theta n cube. Now, h u v is the time taken to go from u to v. Clearly, C u g is going to be greater than or equal to h u v. H u v is the expected time taken to start from u and reach v. Well, it could be the case that while moving, we have not explored any vertex here. But clearly, if we have covered all vertices, then the time taken to do that will surely be an upper bound on the time taken to go from just u to v. So, C u g is going to be greater than h u v, and h u v we know is O n cube. If we take the cover time starting at vertex v, this is no more than n cube. What we will show is not just for this graph, we will show that for the general graph, any connected graph on n vertices, its cover time is bounded by n cube. Okay. So, cover time, that is our theorem of any graph on n vertices is O n cube. Okay. The proof is fairly simple. So, let us look at cover time a little more carefully. If this was our graph on which we were doing a random walk, okay. So, you start at any vertex and keep on moving to a neighbor and so on. So, let us say that we want to compute C x of g, that is, if you start at vertex x, how much time does it take to visit all vertex? Let us look at a spanning tree of this particular graph. Okay. So, the red edges denote a spanning tree of the graph. So, if we traverse all the edges of this particular spanning tree, starting at x, we are guaranteed that we would have visited all vertex. So, you can write the following: time taken to traverse the spanning tree is going to be surely greater than or equal to cover time starting at x. So, spanning tree, again when we say time taken to traverse a spanning tree, we mean time taken to traverse a spanning tree starting at vertex x. Okay. So, let us just number these vertices in a particular way. This is my vertex V 1, x I am calling as V 1, this is V 2, this is V 3, V 4. So, I am going to traverse the spanning tree in a particular way. So, from here to here and then all the way here, V 4 back to here. If I travel along the blue line, that would mean I visit every vertex twice. So, I have done this in a particular way, and that would have visited every vertex twice. So, 2 times the time taken to traverse a spanning tree is also greater than or equal to the cover time. And I want to traverse the spanning tree in the exact order as indicated by this particular blue line. Okay. So, traverse the spanning tree in this particular order. So, let us say this was the spanning tree, okay, of some graph, and I am starting at this particular vertex and I want to traverse along in some particular order. Okay. So, let us say the vertices are V 0 starting vertex, V 1, V 2, V let us say 2n, because every vertex is appearing exactly twice. So, this is the order in which vertices are traversed. So, time taken to do this, the expected time taken to do this will be an upper bound on the cover time. So, that we will just write down expected time for traversal along the above mentioned path is an upper bound on the cover time. Okay. And this time can in fact be viewed as, let us say I am at vertex V 0 and from there I have to go to V 1. Maybe while I am doing the random walk on the graph, this is not the path that is chosen. From V 0 I might go to some other vertex and after a long time I will come back to V 1. And then from V 1 after some time I will reach V 2 and from there after some time I will reach V 3. Okay. So, let us look at all these as random variables. So, the time taken for the traversal from V 0 to V 1 is the expected time taken is going to be h V 0 V 1. Okay. So, this I will think of as the expected time for the first edge of the tree. Okay. So, the total expected time, if I think of this, the time taken for this path as t, okay, the expected value of t will be the sum of those random variables, and by linearity we can just look at the sum of the expectations, and each of the individual expectation is h is of the form h v I plus 1. Okay. So, the expected value of t or the expected time is going to be less than summation over all these i's h v I, and note that h v I plus 1 would appear on, let us say, this particular, this is v I plus 1, and later on, or if we had taken this as I and this is I plus 1, this edge would be traversed in forward as well as in reverse. So, all the edges are appearing in pair, and therefore, this random when we look at this random variable, we have terms of the form h u v plus h v u, one such pair for each edge of the spanning tree. So, the total time taken, if we denote it by a random variable t, the total time taken is equal to the sum of these random variables, and therefore, its expectation is going to be sum over all the edges in E. So, if this edge E is equal to u comma v, then this is the sum over terms of the form h u v plus h v u. Okay. So, what we know, what we have shown so far is that the expected time taken to traverse along this particular path is going to be sum over all edges h u v plus h u v plus h v u, and h u v plus h v u from our last class we know that that is going to be equal to m times r u v, okay. And r u v, note here u and v are two edges which are connected. So, their effective resistance is at most 1. Okay. So, this is going to be less than or equal to 1, therefore, this quantity is less than 2 m times 1. Okay. So, this the number of edges is going to be only n minus 1 because it is spanning tree. So, n minus 1 into 2 m is going to be the time taken to traverse the spanning tree along this particular path. Okay. So, 2 times m times n minus 1 is an upper bound on the cover time. So, if we start at any particular vertex, we can do the same process. So, this is an upper bound on the cover time starting at any vertex, and therefore, this is an upper bound on C g, okay. And m is at most n square. So, we know that O n cube is an upper bound on the cover time. Okay. We will use this fact to construct a randomized algorithm for ST connectivity. So, we have a special situation here. We have a graph which is very large, and we want to know whether two vertices S and T are connected. Okay. So, further we want to do it without using too much space. We could of course use DFS and solve this problem, but when we use DFS we have to store the entire graph, we have to rework, our data structures are going to take space, and that requires O of n space, that is it is going to be proportional to the size of the input. Here let us assume that there is a read only input tape on which the entire data, the entire graph is stored, let us say in adjacency matrix format, and we can query whether some particular edge I and j are connected. So, this query can be done quickly. Okay. We are not expected to use additional memory. So, without using additional memory, or let us say we are allowed to use c times log n, c is some constant, c times log n amount of memory. So, can you do a log space computation for ST connectivity? That is, I want to say, I want to have an algorithm which will check if vertices S and T are connected. The algorithm will not use more than say 1000 times log n amount of memory. The algorithm is simple. We will just start at a particular vertex and keep on going to one of its neighbors. Okay. So, we can just toss a coin and select one of its neighbors at random, and we go to that. Okay. We do not remember as to which vertex we were in, let us say, previous steps. We just keep tab on how many vertices have been visited so far. Okay. In other words, we will do random walk, say randomly walk on G for 2 n cube steps starting at S. At any stage, at any point, if you have already discovered T, if T is found, say connected. If you do not find it, in the end you will say, okay. So, after 2 n cube step, if you do not find T, then you will say that they are not connected. Okay. Of course, if you are given an input where S and T are not connected, this algorithm clearly gives the correct answer. Whereas, if S and T were indeed connected, we want to say that with significantly high probability, the algorithm would return the correct answer. Now, from the previous analysis, we know that 2 m times n minus 1 is the amount of time taken, is an upper bound on the cover time. Therefore, in those many steps, it would have covered all the, I mean the expected steps taken to visit all vertices is 2 m times n minus 1. So, that is something like n cube, okay, it is at most n cube. So, if you just apply Markov inequality, so which would mean that the probability that there is some vertex which has not been discovered even after spending twice the expected number of steps. Okay. So, that probability will be by Markov inequality be less than or equal to half, and therefore, this algorithm gives the correct answer on the S instances with probability at least half. You can make this 200 n cube, and then the probability would be significantly higher. Okay. Repeated runs in this algorithm can make the algorithm give more accurate answer. We will stop here. We will in the next lecture see more properties of random walks. We will see properties called as rapidly mixing random walks, etc.